This is the video for pre-lecture 20. So we've introduced the partial differential equation methods for solving using an implicit or explicit Euler or Crank-Nicolson approach. We're going to continue looking at different ways that we can develop finite difference equations. And so one of these ways is to actually use multiple types of finite difference approximations of our spatial derivatives. So it turns out that it's often better or more accurate, and particularly more stable, to use an upwinding or a sided approximation to approximate our advection terms. So anything with like a d phi dx or a d phi dy, if we were moving in that direction, those terms are going to be better approximated using a sided finite difference, assuming we know which direction the system is moving. So if c is positive, moving from left to right, we want to use a backward approach. And if c was negative, we would want to use a forward approximation. And in fact, what you can do is you can actually have an if condition in your function which determines the direction that the fluid is moving and have the appropriate finite difference approximation made. So for this problem, what we're going to do is we're actually going to use the sided approximation. In particular, we're going to use the backward approximation, making the assumption that c is positive, for just our d phi dx term. And we're going to use a centered approximation, which is potentially more accurate, for our diffusion operator. And we're going to do this using an implicit Euler scheme. So if we just start with our implicit Euler equation, that's going to be our phi n plus 1 is equal to phi n plus delta t times d phi dt evaluated at time index n plus 1. We can make our substitution then. That d phi dt is equal to minus c d phi dx plus kappa d squared phi dx squared. And again, we're evaluating at time index n plus 1. So now this is where we make our spatial derivative approximations. So this is going to be phi n plus delta t. And if we wanted to, we could actually write this in our matrix operation representations. This would be something as simple as c times d1 phi n plus 1 plus kappa d2 phi n plus 1. And then we could rearrange if we wanted to, and we could get something to the effect of our identity matrix, which comes from our phi n plus 1, which sits on the left-hand side by itself, plus cd1, where we would probably make sure that d1 matrix was generated using a backward approximation, minus kappa times d2 times our phi n plus 1 is equal to our phi n vector. So that's a matrix representation of this. But to clarify our finite difference approximation, let's go ahead and make that substitution. So we can say at this point that phi I n plus 1 is equal to phi I n plus delta t times minus c, now times our derivative of phi with respect to x using a backward approximation would be phi I minus phi I minus 1 divided by delta x, and both of these are evaluated at n plus 1 time index, plus kappa times our second derivative approximation, but this time we'll use a centered approximation. So this would be phi I minus 1 minus 2 phi I plus phi I plus 1 all divided by delta x squared. And again, all of these are going to be evaluated at time index n plus 1. And so I should note I'm missing here my delta t's for both of these terms. Okay. So if we wanted to make the approximation or our substitutions, alpha is equal to c delta t over delta x, and kappa is equal, or sorry, beta is equal to kappa times delta t over delta x squared, we can rearrange our equation and get the following. We would have a minus alpha minus beta times phi I minus 1 n plus 1 plus 1 plus alpha plus 2 beta times phi n plus 1 minus beta phi plus 1 n plus 1 is equal to phi n. So, for the problems that we'll be dealing with in this class, we'll explicitly tell you what type of finite difference approximation you should be making for each of our spatial derivatives. But it is something to keep in mind that using an upwinding scheme is generally better for those affection terms in terms of keeping your system more stable. Let's talk about another problem. What if we have a nonlinear partial differential equation? So we discussed last time in lecture that to deal with the nonlinear aspect of a PDE, we would just use the same methods that we would use to solve a boundary value problem that was nonlinear, meaning that we would do the guess and correction type method. So this is an example of what's called the Inviscid-Burgers equation. And so this is our unknown in this case is not phi but u, and so u represents a velocity. And so you'll notice it sort of looks like what we would expect from the left-hand side of something like a 1D Navier-Stokes equation. So we can derive finite difference approximations for this using a couple different approaches. So let's start with the explicit approach, which we'll see ends up being a little bit more straightforward. So explicit would say un plus 1 is equal to un plus delta t times du dt evaluated at time index n. Making our substitution then is just as easy as delta t is equal to minus u du dx evaluated at time index n. Okay, so, well, what would this be? This would be u of n plus or minus delta t times u of n times du dx evaluated at time index n. And we could actually write this in matrix form. Un plus 1 is equal to un minus the diagonal of delta t times u of n times our D1 matrix, whether that be a backward approximation or a centered approximation, probably a backward approximation, times our un vector. Now, this is an example of a nonlinear PDE that we could actually just plug in, because if we consider the terms that are known, everything at our end state we would say is known. Everything that's unknown is our n plus 1 state, and we have that only on one side. So yes, it's a little bit more awkward in terms of generating our big B matrix, because our big B matrix now contains something that has a un in it. But it could be done. So we would say that big B is then equal to our identity matrix minus the diag of delta t times our un vector. We could then take that big B matrix, multiply it by our un vector, and that gives us our un plus 1. So doing an explicit solver for a nonlinear PDE is relatively straightforward. It doesn't require iterations at each individual time step. If, however, we made an implicit Euler approximation of this FDE, then we run into trouble, because then we have something along the lines of un plus 1 is equal to un minus delta t times un plus 1 times dun plus 1 divided by dt, or times dt. And now we have unknowns all over the place. We have unknown on the left-hand side and unknowns on the right-hand side. And there's no way, once we rearrange this, I can't produce an A matrix times a un plus 1 vector where A is not a function of un plus 1. Our coefficients are forced to be a function of un plus 1. So this causes a problem. So in order to work around that, we have to create our guess and corrector situation. Okay, so what we'll do is we'll say, okay, well, I'm going to come up with a un plus 1 is equal to some guess, ug, plus a correction, zeta. And I'm going to plug that into my equation. In fact, before I do my matrix representation of this, I'm going to make that substitution. So that's going to give me ug plus my correction is equal to un minus delta t times ug plus my correction times dug dx plus my derivative of my correction term dx. Can expand that out. And get the following. And so what we'd see is, okay, well, I only now have one nonlinear term with respect to my correction, and I drop that term. And I can rearrange where my unknowns now are my correction terms. So I can rewrite as the following. Okay. So again, let's just highlight my unknowns. My unknowns are going to be my correction terms, like following. I am probably going to want to rearrange this term in particular so that my zeta term is the last thing that shows up in the term, so I can write the matrix representation of this. But taking un as known, taking ug as known, everything on the right-hand side then we can solve for. So I can write a matrix representation of this as the following. My identity matrix comes from this zeta by itself, plus delta t times the diagonal of my D1 matrix times my UG term. That takes care of this term here. Plus delta t times the diagonal of my UG vector times my D1 matrix, all times my correction. That'll take care of that term here. And then the right-hand side, we, again, don't have to be as specific in terms of how we would rewrite this to get it into matrix form. So we'll just continue to un minus ug minus delta t times ug times dug dx. So how would we go about iterating this? Well, we would have for n equals 1 to nt minus 1, we would set our un vector. We would set our ug guess initial to be our un vector. And then we would iterate for I equals 1 through the number of iterations. We would solve for our zeta, and then we would use that zeta to produce a new uguess, which we would then use to solve for a new zeta, continuing to iterate until we've converged, and then take that converged result for ug and set that equal to our un plus 1, and then begin again at the next time step. Okay?